So I want to start by going over common ions. I know we did this in class, but we kind of, I feel like we may have rushed through it. So I want to just go through it quickly one more time. The first thing I want to look at is the ground state electron configurations. I know this is difficult to see on your slides and on the presentation, but from last unit we know that all of the first column have a S1 in their valence shell, whether it's 1s1, 2s1, 3s1, whatever, they all end with an S1 because they have very similar electron configurations in their valence shell. All of column 2, the alkaline earth metals, have an NS2 at the end of their electron configurations. All of column 3A have an NS2 NP1, then an S2P2, S2P3, and so on. We also see within the transition metals some common endings for the configurations. They all have an S2, and then the first column within the transitions, which is column 3B, goes to D1. In the middle we have D5, and at the end we have D10. Those are significant because if we remember, a full valence shell or a full sublevel is ideal. So a D10 would be ideal. The next best thing would be the D5 because it would be half full. And we also know that the lanthanides have a 4F and the actinides have a 5F. So this isn't just by coincidence that they all look alike when we write them out. It's because their electron configurations are all very similar in the highest energy level. So we looked at what happens when some metals try to achieve the noble gas configurations. So we see that sodium loses its S1, becomes a sodium positive, and looks just like neon's configuration. Calcium loses its two S2s right here, and then becomes a 2 positive, and it looks just like argon. And then aluminum would would lose the 3 electrons that are the S2P1, taking a 3 positive charge, and it would look like neon. Remember, cations are positive. Metals form cations when they lose valence electrons. On the other end of the spectrum, and remember, hydrogen can gain one or lose one, but in this case we're looking at it gaining an electron to create a full S shell to look like helium. Fluorine having a 2s2, 2p5, if it gains one electron, it will become a negative, creating a full octet, so it mimics, or it looks just like neon in the electron configuration. Oxygen, which is in group 6A, has 6 valence electrons, so it has to gain 2 in order to fill that octet and look just like neon. And then nitrogen, which is in group 5A, has 5 valence electrons, and it needs to gain 3, thus having a negative 3 overall charge, and it will look just like neon. So atoms that gain electrons, which are usually nonmetals, form anions. If we remember, An means not, so they are negative ions, they are nonmetals, and it's called an anion. So it is good to note that the cations, which lose electrons, tend to try to look like the noble gas that is in the row above them, whereas the non-metals that form anions tend to gain electrons so that they look like the noble gas that's at the end of their row. So because of the attempt to look like noble gases, The metals in the first three columns tend to take the charge, the positive charge of the column number. Alkalis in group 1A tend to take a 1 positive because they lose that 1 electron. Alkaline earths in 2A take a 2 positive because they lose both of those S2 electrons. Aluminum and the other metals in group 3A tend to take a 3 positive because they're going to lose all 3 of those valence electrons. And on the other end, when we look at the halogens in group 7A, they just need 1 more electron to look like the noble gases that they are right beside. So they just take in 1 electron. Group 6A needs 2 electrons, and group 5A takes 3 electrons. So this is the common ion for each of the representative columns. Notice that noble gases don't have a charge. They already have that configuration that is ideal with a full octet, or in helium's case, just 2, which is a full energy level for them. The carbons and the other atoms in group 4A, the nonmetals don't tend to take a charge. They would rather share electrons than take a full 4 positive or 4 negative. They're right in the balance, right in the middle with 4 out of 8. So they tend to share instead of take an ionic charge. Whereas the metals down here in the bottom of that column, tin and lead, will take other charges, just like most of the transition metals. So the transition metals, because they have the 2s electrons as their valence shell, but then they also have the d orbitals, they have a little more room to gain or lose electrons. In this case, they're metals, so they tend to lose electrons. Some of them tend to lose these 2s electrons first, but with the d orbital, remember, they're trying to get a full shell or an empty shell, or the next best thing is to try to get a half full shell. So because of that, iron, for example, will take a 2 positive or a 3 positive charge depending on the situation, but it can take 2 positive because it wants to lose these 2 s electrons, or it can take a 3 positive because it loses those 2, and then it loses an additional, so it will have a 5 electron d shell, which means it's half full. And remember, that is the next best thing to full or empty. So if we take a look at the isoelectronics, isoelectronics have the same number of electrons and the same ground state electron configuration. So sodium, aluminum, they both lose electrons to look like neon. Fluorine, oxygen, and nitrogen all gain electrons in order to look like neon. These are called isoelectronic with neon because once they have gained or lost electrons, they have the exact same electron configuration. So it would all look just like neon, both actually with the configuration of the electrons in the energy levels, but also when we write it out, they will all end up looking like 1s2, 2s2, 2p6, which is the configuration for neon. Notice that the positives are in the row below neon and the negatives are in the row with neon. So what I was referring to with the transition metals taking different charges, when a cation, remember that's a positive ion, is formed with a transition metal, the electrons are always removed from the ns orbital and then from the d orbitals. So they tend to lose, in this case iron, the 4s2, they're going to lose the 4s2 electrons, becoming 2 positive. So that changes the electron configuration to 3d6. giving iron a 2 positive charge. But like I mentioned, they can also lose an additional electron from the d orbitals, and that would make it iron 3 positive with the 4s 0, 3d 5, because 5 would be half of 10, so that every electron would have its own individual orbital and no one would have to share. So depending on the situation, iron can take a 2 positive or a 3 positive charge. Manganese has a 4s2, 3d5, so it would likely lose the 4s2 to become manganese 2 positive. This one won't lose or gain additional because it likes to keep the 3d5 as a half-filled orbital. Ionic radius. So we looked at the atomic radius and we found the pattern for that. Now we're going to look at what happens when an atom actually gains or loses electrons and how that affects the size of the atom. So if we were able to plot these, remember we were going to spend some time plotting these. This is what we would get if we compared the positive cation radius to the ground state neutral atom. So as we see lithium, a +1 lithium ion has a smaller radius, much smaller radius, once it loses an electron. The same pattern happens with all of the +1, so this is the alkali metals. All of them, when they become +1, get a smaller radius. When we look at the halogens, however, which gain electrons, the original size of the ion is actually much closer to, the original size of the atom is low compared to the size of the ion. So in this case, as it gains an electron, it greatly increases its size. This is counterintuitive to what we learned with the radius of a neutral ground state atom. Because with that, as we gained electrons, we got smaller. In this case, when we gain electrons, we get larger. It is because now that we have the same number of protons, positives, as we gain an electron, they are attracted to the protons in the nucleus. However, they have more repulsion amongst themselves. So we throw an extra electron in and they actually push away from each other because like charges repel. So when they repel, they actually increase the size of that outer electron cloud. This opposite happens with the positives. When they lose an electron, then there is less repulsion among the electrons, so they can actually get a little bit closer together, which is why they decrease the size of the radius when we have a positive cation. Here is an example of lithium and fluorine. Originally, lithium is large and the fluorine is small. When the lithium loses an electron, there's less repulsion, so it actually gets smaller in size. But the fluorine takes on that extra electron, so those electrons get to push away from each other and make the fluorine larger. So a cation is always smaller than an atom from which it formed. And an anion is always larger than the atom from which it is formed. That is true whether it gains or loses 1, 2, 3, or more electrons. So here is a picture of the ions and their radii compared to the originals. You can see that the group 5, 6, and 7 that we see on the right are much larger as ions than they were in the regular state. And we can see that the positive cations, especially in groups 1 and 2, are smaller than they were as original neutral atoms. So here's a learning check for each of the following pairs. Indicate which of the two species is larger. So we're going to look at N with a 3 negative or F with 1 negative. We're going to look at magnesium 2 positive or calcium 2 positive. We're going to look at iron 2 positive and iron 3 positive. So strategy is we're going to classify the ions into categories. In 1, they are isoelectronic ions. That means they have the exact same electron configuration with different number of protons. Number 2, they're ions that have the same charges, and they're from atoms of the same periodic group. And 3, ions carry different charges but are in the same atom. So they have the same number of protons. So in case 1, ions carrying a greater negative charge are always larger. In case 2, ions from atoms having greater atomic number are larger because they have more protons. And in case 3, ions having smaller positive charge are larger. So, since N3 negative and F negative are isoelectronic, they both have 10 electrons. N3 negative only has 7 protons, F negative has 9, so the smaller attraction from the nucleus results in the N3 being larger. In case B, magnesium and calcium are both in group 2A, they're alkaline earth metals. So Ca2 positive is larger than Mg2 positive because calcium's valence electrons are in a larger shell, 4, than magnesium's, 3. So that's that same idea as this Russian stacking dolls. It has a higher energy level, so it will always be bigger. And in C, both